great, I'm going to go calculate statistical significance on this like situation that he's giving me, right? And I came
Mhm.
back to him and I said, it's going to take 67 years to reach statistical significance. And he said, okay, so that's not going to work. And I said, okay, well, you just asked me for statistical significance. I don't know what that tells you. You just wanted to know how long it would take, and I gave you the answer, so I've done my job, right?
Hi, everybody. Welcome back to Saturdata, the podcast where we teach as much as we learn. And today we're going to be talking all about statistical testing, everybody's favorite hobby that we all do at home after work.
Sometimes I wake up and I'm like, I'm going to A/B test my coffee today.
Oh my God, I just remembered my favorite story. So I did AP statistics in high school. So for those that are outside of the US, we can take these exams to qualify for real college credits before college. And it's actually pretty cool. There's lots of equivalents in Europe and I'm sure elsewhere that I'm not as familiar with. But my favorite question on the AP statistics exam that I will always remember is one of these, like, it's called a free response question. It's basically a math essay. Again, everyone's dream. And the question is like, okay, if you have this information in a study that you're reading through at home, what other statistics do you need to check the work? And it's so clearly written by like armchair professors that are like, oh yeah, everyone checks the work of the studies that they read at home. Like everyone's going to run through and just, I have the test stat, I have the population size, I have the standard deviation. Let me just run through and make sure they did all the math right. And it's like, they're so clearly out of touch of like these high school students are not going to do that at home.
Like, I don't know. Make sure I'm reading out of the right newspaper. What am I going to do?
Yeah, you may not be following along with like 100-page paper and, doing all the calculations yourself. But that's okay, because all you have to know in the data world for the most part is how to interpret tests and how to convey their value to your stakeholders more than like running through, every single intermediate calculation yourself, right?
I feel the need to like give a disclaimer up front on this episode that like I consider myself a data engineer. I don't consider myself a data scientist. So what I'm if there's any words that come out of my mouth today, like just remember that while I'm talking.
That's good, because there might be words coming out of your mouth.
We're going to talk about enough to be dangerous. Like we're going to talk about some of the important topics. I did work in data science for a little while, so I'll talk about some of the topics that are important enough to be dangerous in it and be able to defend yourself and what you talk about, because it is important, right? That's why we're going to spend some time talking about it.
Yeah, absolutely. And I think one of the biggest difference between like pure data science academic work and data science work at work is that the main question is really like, is this analysis important to the business? And if it's not, you shouldn't have done it. And I think this kind of goes back to some other things we talked about in previous episodes about like pushing back on projects and saying, hey, I need to understand exactly what decision this is going to support, exactly, what outcome this drives. Otherwise, I'm going to push back and say, I'm not going to even do this project, because you don't want to be kind of in a position where you're not affecting the business, because that means that your job and the business have no connection. And then that's a big problem for your career.
You said, I hacked this p-value and got it below 0.05, so give me money. And the business is like, great, but like we gave you this project a year ago and that's not even a priority for us anymore. You were still spending time on that? Why were you still working on that?
Right, exactly. Why did it take you so long? And then also you can't be saying things in meetings like, you can't be saying, the p-value was 0.01. You can't be saying stuff like that, because they're just going to be like, what does P stand for,
What is a p-value? Why did you hack it?
Right. Why wasn't it good enough on its own? I think we've talked about p-values before, but as a little refresher for season 1 version of the p-value definition, a p-value is really just telling us whether something is statistically significant. And what that means is, if our null hypothesis was true, how likely would we get the observation that we found? So like if my hypothesis is that, there are 10 apples in this orchard, and I take a bunch of samples and all of them say there's 5 million apples in this orchard, then there's a very low shot that like the mean amount of apples is 3, because I keep seeing millions. And that's really all it's telling us. So like when someone says statistically significant, it doesn't mean it's important. It doesn't mean it's consequential to the business. It could be statistically significant at the level of nanometers, but like you and I operate at the level of feet and meters. So like who even cares, right? It's really important to understand units and application of your test. But yeah, what were you going to ask?
It's kind of related, right? We're throwing around this word significance, right? And then it's about, okay, but who is this significant to? Right, it's significant to the PhD statistician that's working on the project, or it's significant to the CFO. Like, there's two very different definitions of significant.
Yeah, 100%. And you can think about how, like, in research, really small differences can matter a ton. Like, imagine there's some prohibitively expensive medication, and we figure out that you can use like 10 10 liters less per year and still cure the same amount of people. And now you have like a tiny, tiny amount difference in each dose, but it's making a huge difference practically. Whereas at work, things are just really different. And it's also just much less rigorous because the stakes are much lower. There's a lot of statistical assumptions and kind of distribution assumptions that we sort of gloss over in classical machine learning. Like nobody's checking for homoscedasticity, like, uniform variance in your distribution before you run a linear regression model, simply because, and this is literally a conversation I had with my director of data science back in the day, was like, we do not have any other tools. So like if we say, oh, well, this distribution isn't exactly of uniform variance, homoscedastic, which does not mean gay, it means uniform variance. If the distribution is not homoscedastic, then what? We're just not going to give the client an answer? Like, that's not an option.
Sorry, your data didn't meet our assumptions, so we just couldn't do anything. So here you go.
Yeah, I think if we complained every time the data was bad, I think that nothing might ever get done.
I'd probably be just working not in what I work in.
Totally. Yeah, so I think Sam, before we kicked off this one, you were talking about how a raw p-value result isn't a good enough kind of answer to the problem. What were you talking about there? What else do people have to think about when they're doing p-values professionally?
Right. So this is like a paper we read in grad school, I think, which was it was actually really interesting. But they're like population adjusted p-values, or I guess sample size adjusted p-values. So however, whenever you're doing a test, so the p-value needs to be adjusted for the sample size, right? So your p-value is standard p-value 0.05, which by the way was just completely randomly assigned by some scientist who was like 0.05 seems like a good enough value. So there's really no significance in that 0.05 number. But then there's a paper done on like sample size adjusted p-values, essentially saying that the larger your sample gets, the more likely you are, like you were saying before this meeting, the more likely you are to determine some sort of significant impact, especially with a p of 0.05. So the larger your samples get, the smaller your p-value needs to get, i.e., the smaller value to make things harder to be significant, right? Because if it's 0.05, the more people, there's a lot more chance you're going to detect some sort of difference between two populations or between two samples, because no matter how much control you do to get these two samples to be the same, we're living in the real world, right? And things are messy. So no
Yeah.
two different tests and two different samples are going to be the same, right? It's 0% chance that these are going to be the same, no matter how much you do.
So we'll talk about null and alternative hypotheses, which is all part of hypothesis testing. And this is the type of test that gives us a p-value result. And then also the errors that occur in these tests. And I think we'll talk about how important the business value of those errors are in context of these projects, as well as an example that I'll give you, which is actually interviews themselves. So for hypothesis testing, we're testing two different things. We're testing a null hypothesis and an alternative hypothesis. And this can get more and more complicated the more advanced you get in data science. But essentially, your null hypothesis, it's usually going to be an equivalency or a non-equivalency. And you're going to say something like, Sam typically drinks 3 cups of water a day. So like the variable D that stands for drinks that Sam has in a day, D equals 3 would be my null hypothesis. And then my alternative hypothesis, you could look at it as a lot of different ways, but you're essentially like being anti the null hypothesis. Yeah. So whatever the opposite of that would be. And the complexity here is if I say that cups of water equals 3 as my null, I can have 3 different options for my alternative hypothesis, right? So I can have, cups of water is less than 3, cups of water is more than 3, cups of water is simply not equal to 3. And this is complicated because of the way that distributions work, where like you can imagine if I'm doing a greater than or less than sign, then I'm like highlighting one side of a distribution bell curve. And if I have a not equal, then I'm highlighting the entire bell curve except for 1 point. Or if I have like a less than or equal to, then there's 1 extra point in there from the equivalency. So being able to really design these hypotheses well is super, super important. Because let's say I show a bunch of evidence that cups of water Sam drinks is not equal to 3. That doesn't necessarily guarantee it's greater, right? It could be 2, it could be 1. So it gets really complicated, and you have to really understand how to set up and think about your tests. And that's kind of what this episode is really about. Anything else you want to say on that, Sam?
Right. It's like being very specific about what you want to know.
Right. Exactly.
Like I think that's the foundation of hypothesis, that being very, very specific about what it is you're trying to figure out. And then you have to ask a lot of questions about it, and then, set your null hypothesis right. So that way, like if it's the alternative, does that give you what can you do with that? Right. And then that's like another thing about hypothesis testing. It's like, what can you do with the information? If you're going to go through and actually do a proper test, what are you going to do with it? after
Right.
that.
Right, exactly. And you better make sure you set that up right, because if you're going to make a big business decision that has millions of dollars behind it, you better be asking the right questions, because that's really what data work is. It's asking the right questions most of the time.
Right.
So what can go wrong in these hypotheses with type 1 and type 2 errors?
One of them is oftentimes a lot more costly from the economic standpoint than the other one. Or sometimes, if you're working in healthcare, it can be life or
Right.
death, literally. Like a type 1 versus a type 2 in healthcare could be life or death. So, Shift, tell us, what is a type 1 versus a type 2?
Yeah, absolutely. I think the healthcare ones can be pretty scary. So let's go with a
Mhm.
more chill example that no one's going to die from. So a type 1 error is also called an alpha, and it is when you have a false positive. Then a type 2 error is the opposite. It's called a beta, and it's when you have a false negative. So to give an example, you might have heard that, especially in the tech space, interviews are quite rigorous, right? You might have like 7 interviews that are much harder than the job, to be frank. And they involve live coding, they involve take home projects, they involve things that we talked about a lot in season 1, or season 0 rather. So go check out season 0 if you want to hear more about that. But why do people care so much? Why are there so many rigorous interviews? Because the most expensive resource in a company is its people, right? So they want to avoid what's called a type 1 error or false positive. Hiring the wrong person is so expensive that they will go to all the cost of like getting their most expensive engineers on 1 hour long phone calls for weeks, because that cost is so high that they really, really need to avoid that false positive. So in this case, a false negative would be, hey, we think this person's good for the job, but they're not. That's a false positive. The opposite, a type 2 error, a false negative would be, we rejected this person when actually they would be really good for the job. And I think a lot of us have experienced this feeling that we think this outcome of this interview cycle was a false negative because we really could have been good at that job, but someone was just in a bad mood that day and didn't put our resume through or something like that.
Mhm.
So I think it's a really clear example for people of what a false positive and a false negative is. And in healthcare, like there's diseases involved here where like you can imagine, the COVID test comes back positive, but you're not actually sick. That would be a false
Mhm.
positive. Or like, the COVID test comes back clean, but you actually were sick. That would be a false negative. So really important to think about the domain, the outcome, the money and decisions involved in like what are the implications of those errors.
And have you run into this at all, like in a job or in a project before?
So I will say, I was a data scientist in marketing, and I spent
Mhm.
a large part of that role focused on marketing cars. And the tests I was running were largely logistic regressions in a marketing application called lookalike
Mm.
modeling. So we're basically just taking a sample audience, generalizing it to the US population size, and saying, like, hey, if you're like this sample seed audience, then we'll market the car to you. So I would say the type 1 and type 2 errors there of like, well, if it's a false positive, then like you don't actually want the car, but you are included in the group. It's not the most high stakes affair, and it's
Yeah,
not something we
yeah.
spend a ton of time on. We really just looked for the best kind of semantic matches based on our
Mhm.
criteria. And we would take like the top, whatever, like the top 3 deciles of the distribution that we got, the best matches, we would kind of market to. So I would say that in my domain, it wasn't really a big focus for me. Was it more of a focus for
I
you
was
in healthcare?
I was also in marketing when I was doing data science
Right,
work. Like I only did data science marketing. And when I moved into healthcare and other places, it's been data engineering. But
right,
anytime I actually was one time I was data science in like finance, but and one time in utility. But even within that, it was all really kind of focused on marketing data. Like a lot of the stuff we were doing was marketing data. Yeah, and exactly. So we spent most of our time on F1 scores and like
right,
Lyft, right? Lyft was huge in marketing. But yeah, mostly because if you include someone in a campaign or you don't, it's like it doesn't cost me anything, right? It might cost me half a cent
right.
to send this person an email. So it's not going to matter at the end of the day if like they're included or not. So all like the type 1, type 2 is kind of gibberish for a lot of like data science marketing people. But the lift was like really important. It was like, okay, let's like take our top 10% and like let's send like the communication to them and like see what happens compared to like before versus after or something. Right. So yeah, I would say it's a very similar situation for me. So that kind of gets into in your context, right? Like understand the context in which you work. Because if you're going around like talking to your boss around like, okay, I really think we need to minimize type 1 error here. And he goes, or they go, well, like, why? Like, why do we need to minimize type 1 error? And you're like, well, we don't want to include people in our campaign that don't need to be included in our campaign. And they go, like, well, what do you mean they don't need to be included? Like, everyone's a customer. So we want to
Right.
talk to everyone. So why would we not talk to people? Like, so it's for the business and marketing, it's like very hard to pull off some of those things unless you have a very good idea of let's run this test. Let's run this experiment. Then if you can start talking about those things in that way and making them understand that we want to understand what the drivers are. That's when you get in like A/B testing. But again,
Yes.
type 1, type 2 is not huge for marketing data science.
I think that's actually it speaks to exactly what we were saying because the cost can be really high of a type 1 or type 2 error, or it can be really low. And so we in our careers, we're fully aware of these concepts and we're conscious of them and we assess and we say, okay, so the cost of this is what? 30 cents, I think is what you said. So, okay, so I'm not going to like spend, weeks worrying about this because it's not relevant to the business. So like whatever is relevant is what you should be spending your time on. And the only time that this would really come up in marketing is like if a model was really hard to interpret or really weird in context of other similar models, you might talk to your manager who's been in data science for 10 plus years and be like, hey, should I worry about this? Should I worry about that? And that's when, those questions sort of come up. So I think lift is something that we're really familiar with and something that's going to be relevant to a lot of people starting out in data science and also something they don't learn in school because it's more of a business term. So how would you explain lift to your stakeholders and how would that kind of affect your project?
Got it. So for me, and definitely correct me if I'm wrong here, because we're pulling a cat out of the hat on this one. So for me, lift was we would run a model over the sample that we wanted to look at, or the population if we had access to all of our customers, and then we would, for like what likelihood of purchasing one of our products, right? And then we would organize them in terms of their probability to buy a product, right? And then we would look at our top 10% or our top 20%, and we would say if we were to just focus on this top 10 or 20%, it's kind of like the 80/20 rule. It's like the top
Mm,
20% of our
yeah,
customers give us 80% of our revenue, right? So we really want to focus on the top 20% of our customers. And then that can change they most likely will change by product line, right? When I was working in pest control, right? Every demographic area, but it wasn't always just the customer. Sometimes it could be like the zip codes, right? Because then if it's zip codes, then we can increase marketing in those zip codes for this specific product line. Because if they're already a customer, then we have a lot of information about them. But what we really want to do is target people that aren't already our customers so we can get them buying the product, right? But we
right.
want to know like who around them is kind of like a valuable customer. Or if it could be geographic, it could also be demographic. It could be like, these people, they live in the South, they're above 60, they have two incomes, blah, blah, blah. Like there's all these like different demographic pieces of information we can use. So for me, again, that's what I have for Lyft and kind of how I've used Lyft in my everyday life. But what about you?
Yeah, I think that's exactly right. And just to summarize it in a really general way for folks, lift, to my knowledge, is really just saying if you saw our marketing campaign, then how much more likely are you to take a specific conversion action? Whether that's clicking a
Hmm.
button, signing up for something, buying something, whatever the conversion may be, how much more likely are you based on our marketing? So it's kind of like us measuring our own effectiveness as a marketing science team. And that's what your supervisors and your stakeholders care about because they want to see the value of what you did. And it's again not a technical term, not a statistical term, but something that everyone's going to hit in the marketing data science world. So I think good to kind of cover since it came up. And one of the hardest things about the marketing data science world is that a lot of people don't understand what you do. And I remember I one time had someone come up to me and say like, "Oh, I have all of these behaviors from everyone who purchased this product. Can you run a test on this from the entire population of, you know, everybody who did a certain action?" And I had to explain to her that that's not viable and that we shouldn't be doing stuff like that. But she didn't really understand it. And so she kind of thought I was just saying no to her. And she thought I was like, just disagreeing with her
Hmm.
entire
Hmm.
role. And sometimes it's hard to kind of come back from that. But Sam, can you tell us why that's such a dangerous sort of path to go down?
So this is something we were talking about even before we started this call too, right? It's the statistical testing is meant for when we don't have all of our data, right? When we don't have the entire population, or when testing over the entire or like not testing over, but making assumptions or talking about or running some sort of calculation over the entire population is computationally impossible or very expensive, time
Mm,
consuming, etc., or we just don't have it. Right, there's a
right.
lot of reasons why we can't test over or we can't make decisions on by looking at data from the entire population. I think the most common one is you just don't have that data because you have to go get it from third parties and other sources, or it's just too much. So I think that for me that's the biggest thing, but definitely want to hear Do you have any real life stories from that?
Yeah, I mean, there was the real story that I just shared where
Yeah, yeah, yeah.
someone at my first ever data internship was asking me about, can you just test on everyone who bought this and what their price was, I think, like how much did they pay? And so what would the mean be in
It's
theory?
like
And I said, statistical inference means we're using statistics to make an educated guess, basically. So it's better
mhm,
than just like throwing darts at a wall, but it's not perfect. And that's what statistics
Mhm.
is for. But if we know, if we know the purchases that everyone made, we can
right,
just go in Excel and use the average function and say, okay, what's the mean of this entire population? And so
right.
when you can just count, when you can just take an average of a population, that's the dream. That's like, you don't even need a data scientist for that. I think anybody who knows how to use like basic software can do that. So I think people, and this again, this comes back to my biggest gripe with this domain, is that people think it's magic. It's not magic. It's a tool you are supposed to use in a certain situation. If we're not in that situation, we shouldn't be using the tool. And it's kind of a
Right.
letdown because like people will come in and say, "Oh, I have this project. It's super cool." And you'll have to be like, "This is awesome, but unfortunately, this project doesn't work with this tool. It's a completely different thing. So please just trust me on this."
Sample size is really important here in terms of, and I'm finally back to what I was trying to remember earlier. So hallelujah.
Yeah.
Is one time I was interacting with a business stakeholder in marketing, and he said, I want to run A/B test on the website on 10% of the website's visitors. And I said, okay. And this, I'm like 2 months out of grad school at this point. So I'm like, okay, I'm talking to him about it. And like, I'm coming at this from a very like grad school perspective because I'm still trying to get my like way in the world. And so I'm coming at it very academically. And he's like, how many visitors do I need to the website to reach statistical significance? And this,
Uh,
he was like an SEO guy. So he like knew about A/B testing and he knew about some of this stuff. And so he knew like the word. But because I was still in my grad school mind, like I just heard the word statistical significance and I was like, great, I'm gonna go calculate statistical significance on this like situation that he's giving me, right? And I came
mhm.
back to him and I said, it's gonna take 67 years to reach statistical significance. And he said, okay, so that's not gonna work. And I said, okay, well, you just asked me for statistical significance. I don't know what to tell you. You just wanted to know how long it would take, and I gave you the answer, so I've done my job, right?
So
He
you
was like,
you really needed to stay in that job until like the end of your life, basically. But you're
yeah,
not even there. So how are they even gonna get there now?
yeah, and he was like, well, that's not gonna work, and I was like, okay, what do you want from me? And he was like, well, what else can we do? And I was like, well, we could increase traffic to the website, and then that would get us more visitors, and then we could run the test over more people. And he was like, well, that's not going to work either. And I was like, okay, well, I actually don't remember what we did for the outcome of that scenario. I think at that point I was like pretty like, wow, this is not going to work because it's going to take 67 years. But that goes into like the statistical significance versus the practical significance of it. It's like you don't have a large enough sample because you only have like 100 people visiting the website every day. So if you're going to test over 10%, that's 10 people a day. And then to get into some sort of statistical significance, it's going to take us forever, right? At 10 people a day to try to figure out if this actually matters or not. Whereas companies like Uber and Lyft and Facebook and Netflix, like they have what, right? Millions, billions of visitors.
Yeah.
So they can A/B test like in real time. And that's why a lot of like the data science work at those companies is like when Harvard Business Review came out that like data science was going to be the sexiest job, like that's what they were talking about, right? It's
Yes.
like they were talking about Fang. They weren't talking about like little company over here in Memphis that I really enjoyed working for. Like that was not the people they were talking about at the end of the day.
Yeah, absolutely. And I have mostly worked at B2B businesses until my current role, and I was like, where are the A/B tests? You're selling
Yeah.
to business contracts. Like there's no A/B tests. A/B test is only for B2C, and there aren't even that many tech companies doing B2C at that like you said at that scale. So it's even if you're business to consumer, you have to be so big for this to be impactful. So with that, I think it's a good time to talk about some different common types of A/B tests, and we'll run through these more in depth in the statistical testing notebook resource, which I will probably be running through that with y'all. And so some really good tools that we can use for A/B testing, and then good tips on interpreting and considering how to deal with these things in production. So some really popular ones that you'll want to be knowing about. And all of these are going to be through the SciPy Python package, which is again just like scientific testing in Python. And that's why we're emphasizing interpreting tests so much, because you will not be writing your own test. Like that's a waste of your
Hmm.
time. Don't waste people's time with that. Just know how to read the outputs and apply them, sensibly. So some really big tests that everyone needs to know: independent, two-sample t-tests. And what we mean by independent here is that the groups are not related. So like some tests will be, the same patient took a placebo and then a medication. That would be like a paired dependent t-test. That doesn't come up very much. So you're going to be looking at independent samples of like, okay, group A and group B, control group and experimental group, this very similar format that anyone who has like studied the scientific method for a single day knows this format. So that's where the t-test comes in. This is different than a z-test because we can't always assume that we have a normal distribution. And the z-distribution is a normal distribution. So the t-test is saying like, okay, let's use degrees of freedom and other statistical tools to use this t-distribution that kind of approximates a normal distribution. And that's how we'll be able to infer anything from our testing, because we're going to put these rules on it from real data. And that's where the magic of like theory and practice kind of come together. So then when you're dealing with numbers, t-tests are great. What about when you're dealing with categorical data relationships? Yes, no questions and things like that. Any categorical breakdown of like, okay, does a red dot or a blue dot or a black dot make users click more on Google or whatever, that might come up. So that's where you're going to use a chi-square test. This is again in SciPy. And I feel like there's no point, looking at the actual functions and just like saying nonsense words to y'all out loud, because nobody reads these. Like, the name of the function is like t-test ind, and it's like nobody's reading that. So then you'll be interpreting chi-square statistics and p-values as the results of all these tests. And then there's ANOVAs, which are, I think, kind of underrated. Like people don't talk about them as much, but also extremely, extremely important. And ANOVA stands for analysis of variance. And this is when you are going from a 2-sample test to a multiple sample test. Maybe you're looking at 3 or 4 samples, which again makes so much sense. Like 1 control group and 3 variances of a medication. There's so many, or it would be variations of a medication, but there's so many situations where this is really helpful. And again, no method is better than another. We are not saying you should always use one. These are tools, and we should understand which situations should we use them in. If we have 3 control groups, we could compare A to B, B to C, and then A to C in like 3 different t-tests. And I don't like when people do that. Just learn how to use ANOVA, guys. Like just learn the right tool for the job.
That's what it's built for.
That's what it's built for. And Sam, one of the really popular metrics for all of these tests is the F1 score. And you mentioned that you've used that a lot. I've used that a lot. So why is the F1 score a good metric? What is it telling us?
Man, is it telling us? Is this in our notes?
I caught him on the spot there. I can kind of cover this. So basically, no one metric is good. If someone gives you one metric, they don't know what they're talking about in data science. There's all of these different metrics of like precision, recall, accuracy, specificity, and F1. And what you really need to know is that all of these metrics are emphasizing some balance between the type 1 and type 2 errors. And again, we care about some more than others in different business contexts. So there's precision, which is like the true positives over the true and false positives together. And then there's recall, which is like true positives over true positive plus false negative. So they all look very similar, but it's really just about like, okay, what's different in the denominator and what am I comparing against? And so what's really good about F1 is it's actually the harmonic mean, I believe, of precision and recall. So you're combining the power of 2 of the most important metrics here. And that gets you a good picture of the entire model with one number. Whereas like if you were to use accuracy, it's all the true positives and true negatives over every option. True positive plus true negative plus false positive plus false negative. Accuracy can be really misleading. Like a model might have bad accuracy and still be very suited for like one particular purpose. So F1 is going to give you a much more balanced picture of the model with a single number. But again, you should still be looking at what's called a confusion matrix. You should be looking at all of these metrics at once as a data scientist, and maybe share one flashy number with the whole team or with your stakeholders or whatever. But definitely don't depend on just F1. But it is a good place to start.
It's kind of like the right tool for the right job, again, with the confusion matrix. Yeah, I can't tell you off the top of my head what all those formulas are like you can, but I do know, at least for the confusion matrix, right, we would always know which box we needed to look at for the test we were trying to run or the scenario in which we were working. It was always like, we really want to maximize recall. We really want to maximize precision. Doesn't matter if accuracy is 20% if our recall is 80%, right? Like it was very focused on like one number that was more important than the other. Again, it's been a while, but that part, yes.
Yeah, absolutely. And then the one other test I wanted to share with people is something that we talked about a little bit indirectly already about the Shapiro-Wilk test. And this is used mostly in academic context to test if a data set has a normal distribution. Because again, we're making all these assumptions based on, is the data set normal? So it's probably good to know if that's true. And then we can, do all the statistics on top of it. But again, like we said earlier, we're not actually testing for this most of the time. But there's something called central limit theorem that lets us kind of cheat and lets us use the rules of normal distributions, even if the distribution isn't actually normal. And basically, central limit theorem just says, like, if we have enough people, if we have a big enough n in our data, then we don't care if it's normal because we can approximate it with this t distribution. So just another good thing to remind people of, like, I think every textbook has like a 3-page long explanation of central limit theorem that is really hard for most college students to understand. But the gist of it is like, hey, this is literally just saying that you can still use your model and you can still run your test, even if you don't have a perfectly normal distribution or a distribution that is going to meet every single assumption, because it's good enough that we can then approximate, right?
Right.
Sam is like, I got a lot to say here.
No, I actually don't. I think we learned in grad school the number was 35 or something. It feels like another number that was just randomly pulled out of a hat one day, so probably is not. I don't know how
Yeah,
true that number is.
they ask you to take a lot as a given. They ask you to, like, okay, if n is, I think it's 30. If n is greater than 30, then you can use central limit theorem. And we're just like, okay, great. I
Sure,
wonder how they
cool.
arrived at that. I bet there's like a book about the guy who came to that conclusion.
Like 28 people, 29
Nah.
people, 30. Yeah, that's the one. That's the number.
Yeah, it comes to that, like, what is the marginal difference between all of these things? Like, if your p-value is 0.49, then it's right under, like, or 0.049, it's right under 0.05. Like, okay, was that 0.001% really making such a big difference? And that's where you see that, like, statistics is the closest approximation that we have to truth, but truth can be dicey. And,
Right.
if you set your threshold a certain place, then in one universe it's the truth, and in one universe it's rejected. So that's, I think, another good thing to bring up before we get into the last kind of section here is what's always drawn me to data is, again, this pursuit of truth and the fact that in science we do not prove things. Contrary to popular belief, we'll always say, the study proves this. No, it doesn't. It provides evidence for a hypothesis. So what happens is you have your null hypothesis and your alternative, which is, in some form the opposite of the null. And we say we either reject the null or we fail to reject the null. We are never here to say we prove the null. That's never going to happen.
Right.
And I think that's so great because, like, there are so many things in science that we've been sure about until 30 years later we disprove it. And it's really important that, like, we should be sure in our knowledge. We should operate on the assumption that, like, the scientific theories are true and that the best evidence we have is good. But also, it can change anytime. We can always make new discoveries. And I think that that's a really cool way of looking at things.
So how do you know if when you run that experiment at work and then you get a significant p-value? Sure, let's even say it's like sample size adjusted, right? So you're like fairly sure that this is a significant number, and then you want us to then make the claim that, okay, with the evidence provided, we can sufficiently reject the null hypothesis, right? What do you do with that?
Well, when we reject the null hypothesis, we're just saying that whatever assumption we made is not true. So it would really depend on the decision. So let's say we're studying to see, if we put some amount of money into our marketing campaign, if we have some amount of reach, it will drive some amount of revenue. And we take a bunch of samples and we say, like, oh, we are rejecting the null hypothesis. If we do X amount, it's not going to give us the result we expected. And now we know that we should not be investing in this specific type of marketing campaign, or we shouldn't be, doing the decision we thought might help because it didn't actually give us the result we wanted. So it's like, it really depends, again, on the decisions. And that's why it's so domain specific of, like, what should you do? That's what your stakeholders looking to you for information about. And so if you don't know what to do, then the whole system is kind of broken because you're the one who's supposed to know, like, okay, based on this information, what decision are you recommending? Because you're an advisor. Like, you're an advisor to your stakeholders in the data world, and they are just taking your word hopefully based on the most mathematical, statistical assumptions that we can make. But at the end of the day, that's what you're there for.
And that's why how you approach the entire scenario is really important. Like how you set the hypothesis. What is your null hypothesis? Is it greater than? Is it less than? Is it equal to? Like all of those things that maybe like feel not so important. I think once you start asking that question of like, okay, go all the way to the end. Go all the way to the end. Say you reject the null hypothesis. What are you then going to tell me as the business to do with that information, right? And I think maybe that could help a lot of maybe early data scientists consider if they're being tasked with running experiments or helping to set up experiments? Like, what do we do with that? If you make some sort of decision about the null hypothesis, what can the business then do with that? And if you can't give a good answer to that, then change your null hypothesis, right? Like change
Yeah.
what the thing that you're actually testing, so that way you can justify the time and the money that you spent going into that testing, and the business can then actually do something.
100%. This is another engineering technique, actually, I think in disguise, called a premortem, which I'm sure you've done, where basically we sit down with our engineering team and we say, okay, we're about to launch a new feature. Let's say tomorrow it fails. Why? And we figure out like, okay, where are the weaknesses? Where are the vulnerabilities? What tests and other measures can we put in place to kind of protect against that? And yeah, this is how we should like honestly accept or reject projects in data of like, okay, I want you to do this project. Okay, well, if I tell you this result, then what impact will that have? And if the answer is nothing, then actually we don't need to do this project, because no matter what I do, it's not going to matter. And that's like a really good way
I'm
to
going to
assess.
waste my time.
Yeah, exactly. It's a really good way to assess what work is valuable. I think, Sam, you hit on something unplanned that was like really, really powerful there. So that's what we're here for. And then
It was not in our notes.
It was not in our notes, y'all. It was not in our notes. What is in our notes is this last part here about kind of understanding what are the applications of these tests in production and how do we actually interpret them. And so we've talked a lot about the N here, and N being the size of the data that you're using in your tests and in your statistical processes. And there is a situation where if your N is too small, which we might call an underpowered test, then you're always going to find that it's not statistically significant and nothing has changed based on like the experiment or whatever else you're testing. But there's also some dangers in the other situation when N is too big. So what happens there?
But I hit on it earlier, right? Like the N being too big and then just assuming that 0.05 is the right value. And then you just go say, okay, I have 1,000,000 people going up against 1,000,000 people and a control versus placebo. And then, oh, wow, they're different because my p-value is 0.02. It's like, well, probably not. Like with sample sizes that large, if you're confident in the testing methods behind it, right, then you're probably not actually making any significant claim, right? There's probably just some differences that just happened, right? So let's bring our p-value down. Let's bring our alpha down, so that way we aren't just detecting significance all over the board. Maybe in this case, the significance is 0.002, and if you got 0.02, well, now you can fail to reject the null and say like, well, we couldn't detect that there was a necessarily significant difference. And what does that mean, right, then for the business and what we do all?
Absolutely. And the central theme behind that is that like when your N is big enough, again, faying at scale, you're always going to find a difference because there is so much random variation, and the p-value is testing for random variation. So when you allow for billions, there's going to be so much that it's hard to test for because it's just all over the place. So yeah, when N is too small, then nothing is significant. When it's too big, everything's going to be significant. So we have to, lower our threshold for our alpha, lower the p-value that makes things significant. And the other big thing here is the effect size. So effect size is also known as Cohen's D. It's funny because my AP statistics teacher was also named Cohen. Shout out to Mr. Cohen. And so Cohen's D is telling us on a scale of like 0 to 1, or even above 1, actually, on a scale starting at 0 and going up in magnitude from there, how big is the magnitude of the difference between these two variables, these two groups, these two situations? So again, the p-value statistical significance just says we're unlikely to find our observation given the null hypothesis. That is literally the whole thing. It could mean that we all just go back to sleep. We don't care. But the effect size is saying, okay, how much do we actually care about this? How practical is this? Because again, at the scale of nanometers, something could be statistically significant and the effect size can be like a 0.01. And visually, this is measuring like the difference in means between two distributions over the standard deviation that you're seeing. So again, it's really just distributing the difference over the population expectation. So like maybe it's statistically significant, but the difference is 10 and the standard deviation is 100. So like this is well within normal. This is well within normal variation, and we don't actually care about this. So what's really powerful about the effect size is we've talked a lot about N's, and N's are important. It's important to know how much data we have. But what's really cool about effect size is the effect size is going to be consistent no matter what the N is. And we've seen that the N can determine if something is significant, if something is statistically significant or not. But the effect size is not going to change. So this is just as important to our life, regardless of how many people are in that test, assuming it's statistically sound. So yeah, there's a lot in there. There's a lot going on there.
And so that gets into some of the greater context around some of our reporting, right?
Yeah. Yeah, absolutely. So like, what would you kind of tell someone when you're giving them the result of a test? You would tell them something like, we need a 3% revenue increase with 95% confidence. There's a decent effect size of like 50%, and the implementation cost for that would be $1 billion. And then maybe, even though the statistical test is amazing and it's going to have a massive effect, we don't have that budget in the marketing department this year or something like that.
We hit on this in a lot of other episodes too. It's just acknowledging the context and pulling like the academia out of the work we're doing, because we're not just researchers with infinite budgets, but we're analysts, we're data scientists working in this messy business which has a lot of things that they have to make happen, and that I can't just make decisions in a bubble inside of this business. There's other
Mhm.
things that have to happen. And again, I think that really goes back to the importance of like how you set up the test. I've never maybe paid too much attention to it, or didn't pay enough attention to it, and now that we're sitting here talking about this, I think that that's just how I see the success or lack of on a data scientist maybe working in marketing is really going to be dependent on how they set up all of their tests. Because again, if I'm testing something and the implementation cost comes out to be $1 billion, I probably should have known that beforehand about like, okay, if I make this decision, then it's gonna have this result, and that's not even feasible for the business. So I need to not even just test for that.
That's a
So
good
I'm
point.
like learning something myself here about looking back, maybe what I would have done or how I would have changed it.
Yeah. And I think there's a huge difference between like, assuming the business just wants someone who's going to like test everything and try everything. And that's kind of the new grad, wide eyed, naive perspective of like, oh, I'm a data scientist. I'm here to learn. Like, you're here to drive value for a business. You need to
Yeah.
understand like what's in the scope of the business and the budget and all those other factors. So, to kind of bring it home, I think we can talk about some really, really popular things that come up a lot in the space that everybody pretty much knows, which are like regressions and correlations. Do you want to walk us through, Sam, in the last section here about like how would you interpret a regression for real people, and how do you kind of give them something valuable from that, and maybe also give us a little outline of regression to refresh people on that topic?
Like rise over run, slope,
Yeah,
AP physics.
yeah. Tell us about it. I didn't take. Tell me about it.
I failed AP physics, but I took it. It's okay. There were a lot of people in our class. So slope in general, if we're thinking in terms of we have both like a quantitative X and a quantitative Y, we have numerical X and numerical Y, right? It's for every 1 unit increase in X, then Y increases by slope units, right? So it increases by a certain amount. And so what do we put on our X axis and what do we put on our Y axis is also something like there's a lot of different things. And this is kind of the heart of data analysis projects, right? It's trying to chart things the right way to see like what relationships can I find. And of course, when you're doing projects in grad school, it's always like very clear what the X and the Y is because they're telling you. But in work, it's not always so clear. I think a lot of times it'll be there's like in economics, it's like supply and demand is very common in these graphs. So you'll see just the as demand goes up, supply goes up. Or as supply goes
Yeah.
up, demand goes up. And you want to see that kind of one-to-one relationship. So a lot of times in business, what we'll see is like for every $1 that I inject into marketing, how many dollars come from a new customer or an existing customer based on ideally the marketing campaign that I'm running, right? And so you would have targeted. That's where you have your placebo group and your effect group, and you're trying to measure the differences in their slope sometimes between these two groups. But you just really want to see like how much money do I get if I give money? If I give money, do I get money? But that's my very kindergarten explanation of slope and X's and Y's. I definitely would love to hear you elaborate a little bit more.
Yeah, I thought that was great. And also, again, borrowing a really good concept from economics and calculus, which is the marginal value of something. And margin sounds complicated. It just means one more, right? So, like, if there's one more dollar, what do we get? If there's one more lead on the marketing team, what do we expect to get from that? And this is also, again, how hiring happens. If we have one more engineer, how much code do we expect? How many tickets will be closed, et cetera? This is how everything works. So definitely a good thing to keep in mind. So I would say that regression broadly is about understanding the relationship between two different variables. And this is important because there's time series, there's auto regression, which is like, how do we compare this variable and the same variable tomorrow, right? So that's auto, that's self regression. typical linear regression is about two different variables. And what we do is we typically plot them on a line for a linear regression with a line, easy. And we say, okay, if we try to plot this with a line, what is the equation of that line? And some of the components of the equation of that line are the slope, which is, okay, if I add one more number, how much does the other variable go up? And what this gives us at the end of the day as a takeaway is the R squared value. And the R square is literally the correlation square. So you can calculate it from correlation once you have that. And what's great about this is you can literally say, we explain this percent of the variance in Y with variance in X. So when the input varies by this much, the output will vary by that much based on the expected model. And the things to be careful with here are things like third variable problems, right? There's the old example of like, if you give people in third world countries a bunch of TVs, then they'll have money. That's not how it works, but there is a correlation between people who have TVs and nations that are more wealthy. So you want to always watch out for things like third variable, if your initial variables are correlated and such. But R squared is honestly more powerful than it gets credit for because you can literally explain it to a stakeholder in one sentence. So that's pretty powerful. Then we talked a lot about p-values already, but again, this is the significance, the statistical significance of a relationship, not the strength of the relationship. The strength of the relationship is that effect size that we've talked about that lets us compare different studies and meta-analysis and lets us really make generalizations about the real world in the way that p-values simply do not. And again, all of this can be done in SciPy stats with linear regression functions. And I think that's a really good walkthrough of like how you'd interpret regressions for real people. The big assumption also for early career people to hear is that what model you choose has a ton of assumptions. And a big assumption of linear regression is you're telling me that this relationship is going to be linear. And you don't want to do things like that. So when you're feature engineering, for example, there's something called ordinal encoding, where like if I have, if I have 3 different category variables, I could label them as like 0, 1, and 2, and I could put them in an order. But what that's doing is that's saying that like the variable I label with a higher number is higher than another variable. So if I say like red is 0, blue is 1, then I'm saying that blue is higher than red. And I'm kind of imposing that linear relationship. So you'll see this in feature engineering, you'll see this in model selection. And even though the linear relationship isn't perfect, it's a really good place to start. It's a good base model, for example, where like, let's say the real model that I want to do is like something really complicated, like, a random forest with a XG boost and like stacking models on models and all that. But I need something to compare it to. So I'm always going to start with like a linear multiple regression typically. And it's a good first approximation, which typically beats perfect.
I think what I'm hearing from what you're talking about and a lot of the things we've talked about in this session today, other than me not knowing like half these terms we're talking about, the thing I'm taking away from this is pay attention to the right things. And like spend your time on the right things, like and that's different from when you were in grad school. When you're in grad school, the right thing was like, I need to get the right significance. I need to get this p-value down under 0.05. I mean, I think that was a lot of times like your professor prepared a scenario for you that you then needed to find the right variables to get significance. And you do this in work a lot, but you got to be careful too, because the more you're like playing around with things, it's, again, when I keep saying like p-value hacking, like that's what it is. It's like I'm just trying to find like the needle in the haystack to find like this perfectly significant scenario. But what I'm trying to get at here is that, like you said, the models have assumptions with them, but the linear regression is good enough, at least to make the business money. Right, the random forest and the XG boost, and I mean a lot of things, they're not that hard to set up now. But these simple models are easy to explain. And if you start black boxing things, you can't explain it, and then you spend a lot of time trying to explain it when you really could have just said like you could have gotten 3/4 of the effect that the XG boost is getting you from the linear regression, but you saved a lot of time. People understood it. There's like a level of politicking that you're doing inside the relationship now. Earlier, I was talking about how I think setting up the test and the null hypothesis is really important. Like all these things that I think we spend a lot of time on in grad school are not the things that you now need to spend time on when you're working as like a data scientist, whether earlier or later on in your career, right? It becomes more of managing your relationships inside the corporate world, understanding the projects that are going to bring value to the business. And then of course, like you've been really great about nailing some of these technical concepts, right? You need to understand the technical concepts. By I say you, I mean you, not me, because I obviously don't. But you also have to take the seat up above where you're doing your work and say, what can I do to bring value to the business in a way that's sustainable and in a way that actually moves the needle somewhere, because that's how you're going to get recognized, right? You're not going to get
Yeah.
recognized because you got like the craziest model with the best significance. You're going to get recognized because you did it in a month and you did it in a way that people understood. Spoke well about it. Like there's all these things that you think are not so important are actually the most important things to get you on the right path wherever you're working at when you're working on things in data science.
Yeah, I think the explainability and marginal value that we've hit on these last couple minutes are the most important thing. Let's say that my linear regression has an F1 score of 82%. That's really good. I could even stop there.
That's
Let's say
amazing.
that's amazing. Thank you. I did a great job.
That's incredible.
Let's say I go to my stakeholder and I say, hey, I want to spend another 2 weeks doing a random forest. My random forest gets an 86% F1 score. Guess who's not impacted at all? My stakeholder. But I just wasted a month of their time.
Unless I can tell you that for every 1%, it's going to make you another $100,000, right?
Which you can't.
But
That's not something
which
you
you
can.
definitely
Yeah,
cannot
you
do
cannot
that.
infer that, by the way. Yeah. So, like, these marginal differences make a ton of sense. And if you were an
Yeah.
academic researcher, that would be important, maybe. But
Yeah.
because you are trying to sell, I don't know, baseballs, it's not the most important thing. So, really, really important concepts to think about. And yeah, just getting the good enough answer for your use case is the most important thing. Almost like an MVP, like a minimum viable product in software.
Yeah.
You're trying to get the best answer the fastest and not have to go through iterations. Like your stakeholder, ideally, they want to meet with you one time and get their answer. They don't want to like meet with you every week and get like a 2% better answer. That's not what they want.
They don't want that. You probably don't want that either. No one really wants that.
No one wants that.
What would you take away from today? Because I think I just gave some of my thoughts, but what else would you kind of take away from this talk?
Yeah, big takeaways from today. I'll throw one new one on there real quick. We just talked about models that give you 80% F1 scores. That is like the highest thing you should believe. In my in my data science internship at JP Morgan, we got a 94%. I think it was 94% precision metric, and that is suspicious. That is indicative of things like data leakage or like third variable problems and multicollinearity and all these things. So be suspicious of anything that starts with a 9. Like if your metric is too high, that ain't good. That's a problem. So I would say like 80s are the highest metrics that you should not be suspicious of. That's a really good tip, I think, for new grads. So that's a big takeaway is if your model's too good, then take another look. Other big takeaways from today are, statistics is about making better decisions under uncertainty. It is not about perfection. And again, if you have the whole population, statistics is not the tool for you because statistics is about making an educated guess in the case when you don't have all the population information. Another one is that a concept is a tool. It's not a rule. It's something that you should use in a specific case. And it's your job to know what is the situation I'm in? What tool should I use? How should I approach and define that problem? And that's the real skill that we're trying to pass on here. And then I think, Sam, your biggest takeaway about like what's going to move the needle for the business, what work should you take on, and how are you going to make that impact? I think that people can learn from all of that.
I love it. I think today's been a lot of fun. I definitely need to go open up my statistics book again. An introduction to statistical learning there with Python. It's on my shelf. Need to go open that book back up. That's what I'm realizing after today. But we have some good takeaways from this conversation. I've had a lot of fun talking about it. I hope you have too. I had a good time today. I hope you did too, Shift, specifically you, and then also everyone watching. And definitely feel free to slide in my DMs and be like, Sam, you don't know anything about statistics. I think that's fine. Nah, but we'll be back next week with some more amazing topics for you. Again, thanks for your time and have a great week, everyone.
Have a good one.
Bye.